Jai Hind, myself Dr. Ajay Pratap Singh, and today I teach here that is the hydraulic power plant. Basically, what is the purpose, how to select the hydraulic power plant, what is the basic criteria of the power plant, where the hydraulic power plant is usually installed. I will discuss one by one what is the uh, specific speed and which type of the turbine is used according to the availability of the head or maybe the discharge. So, we can discuss the one by one. Now, come to this, you can see here that is the hydraulic power plant. We can say if we produce the electricity with the help of the water, so we can say that is the hydraulic power plant. So, hydraulic power plant where where it is possible, that is the hill area is there. So, we can say that is the these are the dam, and the water comes from the penstock, and then penstock basically is the way to transfer the water from one place to the another place, and we can say that is these water will strike from in the blade of this turbine, and basically we can say that is the energy conversion, that is the potential energy. Here you can see that is potential energy is converted to the kinetic energy, or maybe some all potential energy will kinetic energy in terms of some the turbines. In case of the Pelton turbine, or maybe some potential as well the kinetic energy, both are available. So, you can say the reaction turbine. So, these energy will transfer according to the water is strike on this plate, and the water is strike on this blade, and this blade will be rotate basically, and after that the rotation of the hub or maybe some blade, after the rotation, that is connected with the alternator, and these alternator will generate the electricity, and after that you can transfer from the electricity from one place to the another place basically. So, we can say in this case in the hydraulic power plant, you can see these are the general layout, and in this figure you can find out that is these are the dam where to store the water, huge water of the storage, you can say, and these are the available in the hill areas. Basically, the hill areas, why the purpose is that is the source of the water come from upper to lower down, and that is we can say one side is the hill, and second the second side that is the we can say the khadi is there. So, we can say uh, to stop the water from the one place, you can stop the water here, and these are basically you can say the storage of the water. Okay, and after that we can say these storage of the water will transfer from the pipe. From the pipe we can say these are the penstock basically, and the penstock, the material of the penstock is you can say that is the concrete, or maybe some MS plate is there, MS pipe is there. So, FRC fiber and concrete is there. So, we can say these are the water transfer from the one place to the another place with the help of the penstock. Carry the purpose is that penstock is carry the water from one place to the another place. After that, these are the potential energy here, that is the potential energy there. The whole potential energy is converted to the kinetic energy in terms of the Pelton turbine. Basically, here you can place the different types of this turbine according to the availability of the water at the inlet, that is on the basis of the classification is there. First of all, you can say that is according to base of the head, we can say. So, according to the head of the available, these head basically you can say according to head available. So, if the high head is there, then the Pelton turbine is there. Okay, in the high head we can say high head. For the high head is Pelton turbine, and for medium head and low head, and low head, that is medium head the Francis turbine and low head the Kaplan turbine. So, these are basically you can say that is the classification, the basically the three types of the classification you can say, or maybe some energy available, that is the potential energy, whole potential energy is converted to kinetic energy. So, we can say that is the the Pelton turbine, you can say, or the potential energy as well as the kinetic energy, that is the reaction turbine. So these are the different types of turbine. And the reaction turbine, there are the two parts. One is the Francis and second the Kaplan. So these are the basic criteria for the selection of this turbine, on maybe either on the basis of the specific usage, also on the basis of name of the originator also. So I'll discuss the one by one. The main parts of this in this power plant you can see here. The main part is one is that is the turbine. Okay, main part is the turbine. Then the penstock, then dam. Here you can make the dam. Then after that, the connected this turbine is connected with the alternator, and this alternator will generate the electricity from here, and that is the tail race of the water. So these are the main main component of this hydraulic power plant basically. So you can see here that the general layout, you can see, find out the head. So you can find out here that is here that is the dam. Okay, and these are penstock. This pipe is the penstock. Penstock, and these penstock, and one is here for the nozzle, right? The nozzle is moving from forward and backward direction to controlling the movement of this water, how much water is flow or strike on this blade, right? These are the blades of this turbine. These are the runner. These portion you can say that is the runner, and the water is strike on this plate or strike on this blade, and we can see here after that, that is it is rotating in this direction. So these are the rotating like this. After that, first one is impact on this, second one, third one, and fourth one, and that is continuous movement is there. So after that, you can see that is movement like this. Okay, and these are the continuous, and after the strike of the water, it comes from tail race. So drop out the tail race. These are these turbine is shows like the Pelton turbine, or so we can say the impulse turbine. So here you can see that is all the potential energy is converted to the kinetic energy, and these are the casing of this turbine. These are the casing. The purpose of casing is to avoid the splashing of the water. Okay, and these are the shaft of this turbine. These shaft of the turbine is connected to the alternator, and the alternator will rotate. Three phase alternator is there. It convert the mechanical energy to the electrical energy. Basically, you can say here to from you can find out here how the energy conversion is there. In this case, you can see the potential energy is converted to the kinetic energy. Potential energy is converted to the kinetic energy. Whole potential energy is converted to the kinetic energy. It means you can see here that is after the striking of the water, that is the hydraulic energy. Hydraulic energy is converted to mechanical energy, and mechanical energy is converted to the electrical energy. These are the principle of basically you can say the hydraulic turbine, how the energy is conversion. Basically the hydraulic energy is converted, the hydraulic water is strike, the water hydra basically the form of the water is strike on this. So the hydraulic energy is converted to this mechanical part, and this mechanical part and the shaft is connected to alternator. So alternate after the shaft is connected to the coupling with the alternator. So the mechanical energy will generate the convert to the electrical energy. The form of the energy is there, that is mechanical energy, hydraulic energy to the mechanical energy, and mechanical energy to the electrical energy. These are the form of this hydraulic power plant, how the hydraulic power plant is working. So here you can find out another points in this figure. First one is HG. Here you can see that is from here strike the water. So you can find out, or you can see here how the head is calculated. So we can find out here that is the Hg is the gross head, basically total head, how much is head is there. So Hg is the gross head. Here H is the effective head, H capital H equal to net effective head. Net effective head, and HL is the head loss in this pipe, head loss in the pipe, basically the water transfer from this penstock, so that is the head loss in this pipe, or you can say that is head loss during this nozzle, or head loss during this after starting there are some losses there. So how to calculate the total head? So net head, or we can say the net oblique effective head capital H equal to gross head Hg minus total losses. Total losses means like head loss in this pipe, head loss with help of the blade, where the head loss with the help of this nozzle. So we can say total losses is minus in the gross head. So we can find out the net effective head. These are the basic general layout of this hydraulic power plant. So in this case there are some consist of the following. You can say a dam is constructed, we can say across the river or a channel to store the water, and this reservoir is also known as headrace. So we can say the dam, we can make a dam throughout this across the river or the channel, and then we can store. After that dam is created, that is a huge store of the water you can store, and then after that storage you can transfer the water through the penstock, or you can say that pipe. So the large diameter of pipe, you can say the pipes of the large diameter is called the penstock, and which carry the water under the pressure from storage reservoir to the turbine, and these pipes are usually made for the steel or reinforced concrete. So turbine having the different vanes or bucket or blade mounted on the wheel, and the where the bucket is mounted or the blade is mounted on this wheel, we can say that is the runner. In case of the pump, we can say same, the blade is mounted on this, we can say that is the impeller. So the fourth one is that is the tail race, which the channel carrying the water away from the turbine. After this striking the water, you can see in this figure. So you can find out. So the water after the striking that comes from like directly, we can say the directly move from the tail race, or we can these are or we can carry this water through the different types of medium that are called some different type of the duct are using. So different type of the ducts are using. So in these are different type of ducts, you can say we are using the reaction turbine to maintain this pressure. So in case of the tail race, you can see that the tail race which is the channel to carrying the water away from this turbine, away from the turbine. After basically you can say the water has worked on the turbine, and the water surface is the tail race is also referred as a tail race, and this tail race is created through, we can see in this figure, this tail race is created to find out, to calculate the total head or total losses. So we can find out the total losses is there. So include this, the losses in this blade, losses in the nozzle, after dropout the losses is there. So all losses in the losses will added when we can calculate, or I can calculate for the net effective head. So we can consider all these losses of this head. Now the important terms is there, that is the one is the gross head. The gross head is that is the vertical difference between head race and the tail race, and the net head is the net head or effective head is the actual head available in the inlet to the work on the turbine, and that is H equal to is denoted by the capital H, and the H equal to Hg gross head minus total losses. Then where HL is the total head loss during the transit of the water from the headrace to the tailless, which is mainly head loss due to the friction and the giving by some blades. So, we can neglect all these losses. So, you can see here that is the schematic diagram of the hydraulic power plant with the surge tank, and here we can see that is the reservoir. You can see here that is here the reservoir, and these are come from here. One is the surge tank, these are the tunnel, and these are the tunnel valves and chamber here, and these waters come through the penstock, and here you can see that the turbine is here, and that is you can say that is the draft tube is here, and that is the generator on the one part, and that here is the tailless. After the draft tube you can see here in the water available from the tailless is come from the tailless, and this is the lower of the pool. So, these are basically the schematic diagram of the hydraulic power plant with the surge tank, and what is the purpose of the surge tank I will discuss in later. So, these basically we can say these parts I will discuss in earlier in the previous. So, we can see the surge tank in come to the basically next after 2 slide I will discuss the surge tank. So, you can see here basically the difference from the first figure and the second figure here. So, you can find out here, just we will see here that is no draft tube is here. Okay, there is no draft tube this point. The water is directly come from the tailless, and you can see in this figure, and you can analyze here that is water after the striking comes from some medium is there. So, these are the medium, and this medium is called is the draft tube. Draft tube. What is the draft tube? The draft tube is, we can say that is the one expansion device is there, like some different types of is there, the conical type is there, some elbow type is there, and this draft tube purpose is that is the inlet of this draft tube. The inlet size is very less and is the expansion device basically, you can say. Here you can see to maintain the pressure losses during this in case of the reaction turbine, in the case of Francis and Kaplan turbine. Different type of draft tube is available, and the size of huge size of there, and that is depends upon how much pressure is there. According to that he will maintain all this pressure. So, what is the necessity of the surge tank? You can say the surge tank is to perform a hydraulic turbine. It is strongly influenced by the characteristics of the water conduct that needs the turbine, and basically you can say the characteristics of the characteristics includes the effect of the water inertia, water compressibility, and the pipe wall to elastic in the penstock. So, the hydro electric turbine present a non minimal phase characteristics due to the water inertia, and which means that change in the gate produce an initial change in the mechanical power which opposite to the one requested, and the water compressibility, we can say the water compressibility compressibility effect produce traveling waves of pressure, and is usually called the water hammering. So, the water hammer is characterized by a sudden high pressure ridge caused by stopping to flow too rapidly, and the wave propagation speed is around 1200 meter per second. So, in those plants where the distance between the foreway or the reservoir and the turbine is quite large, the surge tank is usually utilized, and surge tank is usually you can say the utilized, and the function of this tank is to hydraulic isolate the turbine from deviation in the head produced by the wave effect in the conduct. Some such tank include an orifice whose the function is to damp and absorb the energy of the hydraulic oscillation. So, these are some functions of this the why such tank is required. And now come to this the classifications of hydraulic turbine. So, we can see here the hydraulic turbine is the two types basically. One is the impulse turbine and second is the reaction turbine. The impulse turbine, we can say that the Pelton turbine is there, turbo turbine is there. In the case of the reaction turbine, that is the Francis turbine is there, the Kaplan turbine there, the propeller turbine is there. So, these are the basically we can say the general classifications of this hydraulic turbine, but the based on the flow, which type of the flow is strike and the inlet, and how the outlet of this flow is there. So, according to the flow of the direction, the turbine is classified the tangential flow turbine, and this turbine is called that is the Pelton turbine. Pelton turbine. Radial turbine is basically we can say that is the Francis turbine. This turbine is not used. Axial turbine we can say that is the Kaplan turbine, and mixed flow turbine is again that is the Francis turbine. Basically, we can say that is the tangential flow, the water enter inside, that is, so these are called the bucket. When the bucket, these are the bucket and water is exactly in this tangential direction. So, we can say that is the tangential flow turbine. When water enter in this side of the runner, so suppose these are the runner and these are basically blades. In this case, the water strike on from here to here. So, that is on the bucket, these are basically you can say the tangential strike is there. Second, that is if the water inside this side, that is the radially enter is there. Okay. And after that axial, the water axially enter in there outside of actually outside, that inlet is from the axially and outer from the axially. So, that is called the axial flow turbine. And from the mixed flow turbine is there, that is the water enter inside the runner, that is the axial radial, and outside of this out from this that is the from the axial direction. So, these are the basic classifications of this the hydraulic power turbine. And basically you can say one more point of this is the specific speed. On the basis of specific speed is the turbine is also classified, and the specific speed we can say is the when you select the turbine is the very important and play a vital role for the selection of the turbine with the help of the specific speed. So, the specific speed is it is defined as the speed of the turbine which is an identical in the shape, geometrical dimension, blade angles, gate opening with the actual turbine, but of the such a size that it will be develop unit power when working under the unit head. So, these are developed for the working for we can say that it developed for the unit power unit head, and this is the speed at which the runner of a particular diameter will be developed for the 1 kilowatt power under the 1 meter head. So, NS specific speed is represented by the specific speed is the NS, where equal to NS equal to N into root P upon H k power 5/4, where you can say where N is the speed, RPM rotation of this runner, then P is the power and H equal to head. And the specific speed is an important factor to governing the selection of the type of runner best suited for a given operating range. And the impulse turbine or a Pelton turbine you can say have a very low specific speed relative to the Kaplan turbine, and the specific speed of Francis turbine lies between the impulse turbine and the Kaplan turbine. So, on the basis of the specific speed, the Kaplan turbine is the very high, and the low specific speed of this, that is the Pelton turbine is the very low. So some parts we can say that is when the rain water falls over uh, the earth surface, it process the potential energy relative to the sea or ocean towards which is the flow, and it can be certain point falls through an appreciable vertical height, and this energy can be converted into the soft work. So as the water falls through the certain height, its the potential energy is converted to into the kinetic energy, and the kinetic energy is converted to the mechanical energy by allowing the water flow through the hydraulic turbine to the runner, and this the mechanical energy utilized to run an electric generator which is coupled to the turbine shaft, and the power developed in this manner is, you can say, P equal to WQH into efficiency. So here you can say find out the power P equal to W, the specific speed weight of the water, and then Q equal to the rate of the flow of the water, and the H equal to the height of the fall of the, or we can say the head, and that is the efficiency sign. So efficiency of conversion of potential energy into the mechanical energy. So the hydraulic project are developed for the following purpose, you can say to control the floods in the river. Second one is to generation of the power, the storage of the irrigation of the water, and storage of the drinking for water supply. So these are some the hydraulic power project developed. So we can say that is for the, you can see here the from the clouds, the water comes from the clouds, and you can storage in the lake or maybe some pond, and after that the sun in burning, then it evaporate and again go to the clouds, and then after that the move rain after the snow, or the snow fall or raining, so you can again come to this. So these are basically the way of how to water receive from the clouds or maybe some from the snow. So basically these are the basic criteria, basic purpose for the collection of this, to how to hydraulic power plant is working. And the water from the site is considered for development of the following factor must be had through analyze. The capital cost of power plant is very high, because when you make a dam, so where the when you make a dam on the river, so it's a very critical, basically when transportation is there, a lot of this equipment is required to initially to develop the dam. So these are the very difficult. So that is the capital cost is very high. The capital cost of in erecting them and maintaining the transmission line and the annual power loss due to the transformation and transmission of electric power, since the water power plants are usually situated in the hilly area away from the load center. And third one, the cost of the electric generation compared with the steam, oil and gas power plant, which can be conveniently set up near to the load center. So these are the power water power should consider for development. And the water power plants have the following advantage, which make these suitable for the large interconnect electric system. The first one is, we can say, the plant is highly reliable and its maintenance and operation charge is very low. The power plant can be run up the synchronized in the few minutes. The load can be varied quickly, and the rapidly changing the load demand can be met without any difficulty. The plant has no standby the losses, and no fuel charges. The efficiency of the plant does not change with the age, and the cost of generation electricity varies little with the passage of the time. So these are the some advantage of this power plant. So the hydraulic power plants have the following disadvantage also. The capital cost is the very high. Second is, the hydraulic power plant take much longer in design and execution. Third one is, these plants are usually located in the hill area far away from the load center. The transmission and transformation cost is very high. The output of hydroelectric power plant is never constant due to the varies of the monsoon and their dependence of the rate of the water flow. So these are basically, we can say, the some advantage and disadvantage of this power plant, and these we can say that is how to. So how to essentially features of the water power plant we can see here, and simplified we can terms of the flow chart, and we can find out for that. So the simple flow sheet of the water power plant is shown in this figure. You can see here that is the catchment area. These are the basically the flow diagram or essential flow diagram is there. So these are the catchment area, and these are the reservoir. You can see here from the reservoir, then dam is there, then the sluice gate is there, then penstock to transfer the water from one place to another place, then inlet valve is there, then turbine is there, then switch gear is there, and trellis is there. So these are basically you can say the essential or the flow diagram how to make the power plant in the one line. So these are catchment area, reservoir, dam and intake house, then inlet waterway, powerhouse, and trellis and outlet of the water. So these are the way how to the power plant is working, and how to calculate the water power plants. Basically there are some calculations. So the calculation are concerned with the river or the stream flow and the available head through the waterfall to generate the electric power, and water in motion we can say the process three form of energy, that is the kinetic energy due to the velocity, pressure energy due to the pressure, and potential energy due to the height. So the kinetic energy equal to V square by 2g Newton meter per kg of the water, pressure energy rho by g, P by rho. Basically these are the P by rho, and potential energy G into H, where the V is the velocity of the flow in the meter per second, and P is the pressure, and density rho is the density of the water, and that is H equal to the height of the head or local level of the water from available to above to some datum level. So these are some calculations to how to calculate the kinetic energy, pressure energy, and potential energy. And then after that we can find out that is the Q is the water flow rate, and that is the power. You can say that the power equal to WQH. So we can calculate the power, and where Q equal to the water flow rate, and H is the basically we can say net head, net effective head basically. And if the turbine has efficiency, so we can say that is then the brake power of the turbine of the servo WQH into NT, and this efficiency can be electric generator. If the electric generator efficiency NG, so then the effective power which is on the board is again multiplied by the NG. And after that, if the above calculation is following the relation which used on the discharge, so 1 Qs equal to 1.3 square milliliter per feet per year, and that is 1 foot of the water over one area equal to 1.12 square milli will give a discharge of the 1 comes throughout the year, assuming the runoff of the 100%. So these are some these are discussed. Basically on the power plant, you can say on the basis of head, you can say that the high head power plant is the 100 meter or above. The medium head is the about the 30 to 50 meters you can say, and low head basically you can say the medium head basically you can say that is from 100 meter to the 30 meter, and the low head basically below the 30 meter up to the 30 meter you can say that is the low head power plant. These are some different types of the power plant. Basically you can say here, you can say that is the head race is there, reservoir is here, these are the reservoir from this, and certain position from this here. So the again here that is the dam is this place, and again the water from the on the canal basically. So here you can calculate here that is from the basically in this case basically we can create on the canal. So basically these are the different types the storage of basically we can say the or installation of this power plant in different positions. So these are basically from figures you can find out, and these are if basically these are the basic things about this the power plant, how to calculate basically the head or maybe design of this turbine. So I'll specifically detail in share in the next lecture how the basically the Pelton turbine is working, or the maybe some hydraulic turbine are working in the Kaplan of Francis are working. So and different parts as well. I'll discuss in the next lecture. Thank you so much.